Good day to you. This is Galactic bringing you a presentation on the Boscovich Force Curve, which you will see to our left here. That is a bit congested. Even Roger, in his book where this appears from the 18th century, he comments that this diagram is a little overloaded. Let's get a better view of this same force curve. This is a simplified version of that, showing the ordinate of force, which is remarkably important to understand because the nature of this curve is such. Now you can see the abscissa. The abscissa is space, as you can see written there. The abscissa is the x coordinate line, which we consider to be the x-axis in a two-dimensional diagram of this nature. However, the curved line can easily be misinterpreted, and I myself went through this process of adjustment, so I wish to express to you a strong recommendation that you do what I did not do and immediately master the nature of this curve such that you know what it represents. What is intended to be represented in the Boscovich Force Curve is the relationship between two elementary particles. Physics has discovered those particles, although in Roger's day it was well over a century into the future that first the electron would be discovered to a new threshold, and then the proton, and then the atom. Not necessarily in that order, but you could see they would all be closely related, since the definition of an atom is a combination of electrons and protons in a balanced object called an atom. Atoms are extraordinarily stable, although you have to be cautious because there are on the order of 100 atoms, which are ranked and rated in the periodic table, an excellent diagrammatic formulation of the types of atoms that exist in the universe. They become progressively more complex, of course, as there are more protons. And the definition of an atom is precisely the number of protons. And of course, there's a footnote. The footnote has to do with the presence of an altered state of the proton in the protonic core, which we have come to call a neutron. That is not in view in the diagram you're looking at now, and in order to drill down to get a grasp of what is being portrayed in this extraordinarily profound diagram, we're now going to switch to this simplified view of the inner curve. Now, just to compare, you can see that the curve that goes below the line that is marked C and D, just to the right of the zero ordinate line, is in fact this curve. The nature of this curve is so fundamental that it is extremely important right at the outset to understand what is being diagrammed and the way a 2D graph is first approached in order to explain its meaning is to give the two parameters of the curve in this case. The two parameters are, of course, the x-index and the y-index. In older language, the x-axis is called the abscissa. That's what Roger Boscovich called it. And the vertical index is called the ordinate. there are two lines here, one which is straight and one which is curved. There is a third line which is implied, and that is the left edge of the diagram, which is marked in force terms. So the ordinate is force. That's very important, and this is what I want to give to you in this very brief lecture. We will have a series of lectures covering this curve, so that by the time we're done with this series of brief, about 10-minute lectures each, you will fully understand the Boscovich Force Curve. To begin, we begin with the simplest aspect, which is the x-axis. That is linear spatial separation. That is the formal term for what is most obvious to most students, I should have to say. It's so extraordinarily basic that you will be comfortable with the notion that on the x-axis, it indicates linear spatial separation. Linear spatial separation of what? Two particles. Extraordinarily simple. Now, why is there a curved line? First of all, in order to get at the meaning of this in the simplest and most direct fashion, it is important to incorporate motion. This can best be apprehended in the first pass on the motion of one particle toward another. And so we are going to consider this diagram in terms of the two particles that are in relation. And this shows the relation of two particles at their closest proximity. In this version, you see that it's more extended and that there are a series of curves that attenuate outward from the center. To the left of the ordinate axis is the reflection, because this is a portrayal of spheric space. So there would be a reflection on the other side. The other side of what? The 0 point at the center, where the x and y axis meet, is the center of one of the particles, which is considered to have no velocity. In other words, the inertial frame of this diagram is on the particle, which here is on the left side. It's at 0. That is the standard way of putting a grid over a visual representation. This is in 2D, but it is a projection downward from 3D. That does not materially affect the interpretation of the graph at the most fundamental level. So to begin to see what this means, look at the extreme right of this diagram, and you'll notice that the last curve is left open. That is called an asymptotic curve to infinity. So there is an infinity represented in this diagram. Infinity can only be represented implicitly for obvious reasons. So the open line continues on to infinity. The nature of an asymptotic line is that you have the horizontal line, which again represents space. That is the space line, and it is so labeled here. The abscissa is spatial separation, obviously projected down from volume space into a flat plane where we perceive adequately the relationship in space. So this, the horizontal separation as I'm moving my hands, is in space. The vertical axis is non-spatial. That's extremely important, so it's important to get a firm grasp on what is represented in the vertical aspect. It is a force relationship which on the vertical is being measured as ordinarily it would be positive going up and negative going down. What that means in terms of force would be, in this case, attractive force is positive and negative force, that is below the horizontal line, this index is force strength. So that at the median, there is zero attractive or repulsive force. In other words, no force. And that's interesting because in this diagram you can see that force is represented everywhere. It's represented everywhere in terms of the, I believe that's called the amplitude of the curve, going up so that it makes humps going up and humps going down. That shows that in terms of linear spatial separation, the distance is correlated with the force strength. Therefore, what is represented by the curvy line, where here we are concentrating on the innermost curve, this is the closest proximity of the two particles. This is essentially the force curve of where the two particles collide. Where the two particles collide. Can they? Do they actually collide? Depending on which two particles you're talking about, the nature of the collision between two fundamental particles has a different characteristic depending on which two particles. And so we're forced to ask at the outset, at least in Roger's view, what are the possibilities for the two particles? In his view, since the particle had not yet been discovered, it was being surmised to exist essentially at the quantum level, what we today would call the quantum level, the tiniest measurable separation, either of spatial separation or event separation, which is new, and that is from Albert Einstein, as you know. This force curve will show us the meaning of space-time. Remarkable statement to be able to make, considering when Roger drew this. This particular curve is from Wikipedia on the strong nuclear force, which has an ambiguous definition, but in the article does not. The article is very careful to show that there are two interpretations of that term, because it's somewhat baffling to physicists even to this day. This is ultra profound in the limit of measurability going in. This is a diagram of where our measurements end, where we can no longer measure to any further degree of precision. And another remarkable feature of this diagram is this shows visually the segment in spatial separation where our linear measurement cannot reach. So you're seeing further than the physicists have been able to see, such that they can mathematize what they see. That is called the quantum limit. And on this diagram is the Planck length. And the Planck length has more than one interpretation, depending on what you're considering as being separated. there are now two domains of separation according to space-time formulation, essentially accurate, where not only are we measuring spatial separation, which has been the legacy of science until the modern age, but with the advent of relativity, we are now forced to measure another separation which is non-spatial, and that is called temporal separation. And the space, which is a geometric space, it's unfortunate we are constrained to the word space because it does not mean spatial space in this case. It's a different space called event space. What you'll see essentially on this diagram is a right angle in spherical space. That's what I will be demonstrating so that you won't have to take my word for it. You yourself will deduce it directly. So, what we want to do is follow the flight path of a particle that's approaching another particle. This diagram shows the relationship between a proton and another proton. However, this diagram may or may not represent that. We're not saying, because it might be confusing, and confusion is right out here. We don't want that. The reason I mention that is because this diagram that you're looking at now, which is simply a rendition of this drawing made by Roger himself. In 1763, the Vienna edition was released of Theoria Philosophiae Naturalis, which I consider to be, without exception, the most profound book on physical dynamism, physical mechanics ever published in the history of science. It has gone overlooked, obviously, for quite a while, centuries. However, it's being resurrected. It has been for a number of decades now, and you don't hear about it too much. We won't go into why that might be the case, but here we're exposing a part of science that is rarely seen but needs to be considered now, because this is taken from the Wikipedia article on the strong nuclear force. This is the most important force in technical physics, and I won't go further defining that. Those of you who tune into my lecture series regularly know that I distinguish between two forms of science, one of which is devoted exclusively to technology. So, this is the technological diagram of Roger's curve. It is first remarkable to be able to say that Roger's curve is actually depicted in a state-of-the-art diagram showing the relationship between two protons, which you may or may not know are generally repulsive. They repel each other because they're considered to have the same charge. And in the electrodynamic formulation, that makes sense. So we're going to stick with that for now. Two protons repel and they repel to infinity on an asymptotic curve. In other words, no matter how far those two protons are from each other, there is a measurable force relationship, and I won't say how far away they can be and still be repelling, because you can see that the force curve changes with distance. At this distance, this is the final relationship as they achieve Planckian proximity, where the repelling force is maximal. If you consider the repelling force to be on the negative part of the ordinate, you'll see that the force in the fourth power of newtons is negative below the abscissa. Think of the proton as having a velocity, and it's coming in on the straight line. The relationship between the two protons is linear. It's linear. And that's the horizontal line, is the linear spatial separation. Now, if it's decreasing in distance, we will say due to a velocity of the particle coming in from the right, from infinity. You can see by the asymptotic nature of the curve that it never actually reaches the horizontal line. That is to depict a continuously attenuating force relationship. So it gets less and less, but according to the curve, unless something changes far to the right or further to the right, one must assume that this diagram indicates that the force relationship between the two particles extends to infinity without ever reaching zero. That is both the definition of infinity in one sense, and it's also a couple of other definitions, and you can see it. So let's conclude this. Consider the particle that is here a proton, and as it approaches the other proton on a straight line, the proton never leaves that straight line. That's the spatial line. The dip shows an increase in repulsive force. So essentially, the proton is slowing down. Now it reaches a nadir, a low point, at about 1 femtometer, and then something occurs that's rather dramatic. The force shifts through the through the horizontal spatial separation as the particle approaching the proton to the right, which is at the 0 mark. As this proton, having its own velocity, decelerates, when it reaches the nadir, representing on the horizontal axis the place in its flight where it's being now, instead of being repelled, as the velocity carries the proton further, if the proton has sufficient velocity to get past the maximum repulsive virtual divisor is at that curve going down. If it passes the 1 femtometer mark, the force changes from repulsion to attraction. And therefore, at the 1 femtometer mark, where the repulsive force is no longer increasing, but very quickly stabilizes to the bottom of the curve, shows a stabilization point beyond which the force is attractive. And that's the meaning of the verticality, which is extreme and forms another asymptotic line. The vertical line relative to the asymptotic line skyrocketing upward is not shown here, but it's at the 0.7 femtometer mark, approximately, because we can't be more approximate due to the Planck limit of measurement. But the curve shows it. Even though we can't measure the linearity, we can see it. So that in a very short amount of distance, the attractive force becomes infinite. Infinite attractive force, and that is the meaning of the vertical asymptote. So let's summarize this so we have our first insight into the Boscovich Force Curve which, believe me and stay tuned to hear more, has many more insights to come, but this first one is absolutely revolutionary. The horizontal axis shows the asymptotic relation of a particle with spatial infinity. And the vertical shows the relation of a particle with temporal infinity. Those are the infinities of space and time. This is the transition between the time domain and the space domain. The space domain we know about fully. We see it. We're blueprinted to see space both linearly and spherically. But the temporal domain has been elusive. Some say that it's real, some say that it's not. Neither is perfectly correct because it's superpositional in the strict meaning of that term. What you're seeing is not, strictly speaking, the transition between space and time, although that is correct to say in the linear formulation, as Albert Einstein proved. But the spherical relationship is one step more complex, and that's what's made this so elusive to physicists who have abandoned geometry as a legitimate means of insight. They're going to have to change their ways now, because this is the only way to penetrate the quantum paradox or to perceive the limit of space-time formulation in the EFE of Einstein. So, to summarize this, and now we're going to cut this off in just under a half an hour, because that's the limit, of course. That's important, and I don't mean to make fun of my listening audience, although I very frequently do. It's not against you, it's that I'm seeing into the future. I'm projecting my own path in presenting this formally. Madison Square Gardens is not out of the question. I would step to the podium in a trice. So, what you're seeing here is the transition from the space domain to the energy domain. And that is the correct formulation of space-time, which now you see is not space-time. That's the derivative formulation. This shows the integral formulation, which by definition is the solution. The integration of quantization is shown here. This is the relationship between indivisibility and continuity, such that both terms are perfectly defined in terms of each other. This is the nature of electromagnetism. And the true relationship between space and time, when they're integrated correctly in spheric formulation, which you're looking at, instead of it being space-time, it's space energy. Because energy is a two-component spherical number system. I hope that whets your appetite. This will be fully explicated in the upcoming diagrams, and I hope you enjoyed this. I'm trying to modulate my voice and modulate my temperament, and you see that I'm making some progress. Thank you for tuning in. This is Anagalactic. We'll be right back with you with the secret of the universe.